Hello students, in our last lecture we studied till topic number 9.4 Hooke's law, and according to Hooke's law, stress is directly proportional to strain. Now today we are going to study about topic number 9.5 stress strain curve, means a graph of stress versus strain. Students, you can see here a graph is shown. This line along the x-axis shows the strain, symbol is epsilon, and along the y-axis this line shows the stress, symbol is sigma. So now students, this graph is plotted experimentally, means by obtaining the data from the experiment, the graph is plotted for any metallic wire. You can see here in this figure that experimental arrangement is shown. Here at point A, this wire is suspended simply to measure the change in length of this test wire. Test wire means experimental wire. So the experiment is done on this wire, and when the force is applied to this wire, what will happen? Its length will increase. And so how much the length increases, to measure that, this wire known as reference wire is used. And you can see on this reference wire a scale is attached. This scale is known as vernier calipers. A vernier calipers is an instrument with which we can measure the small lengths. With the help of our normal scale, that is a meter scale, we cannot measure the length smaller than 1 mm. If the length is smaller than 1 mm, then that cannot be measured with the help of meter scale accurately. So for that, vernier scale is used. So here this is a vernier calipers. Instrument is known as vernier calipers, is used to measure even 10 times smaller than 1 mm. It can measure even 10 times smaller than 1 mm. So this is the experimental arrangement. Now after suspending the wires, stepwise the masses are increased in this pan. This is the pan in which the masses are kept. So when the masses are increased stepwise, what will happen? The force F, which is equal to mg, we call that as a weight also. So that force is increasing with the masses, and due to increase in that force, what will happen? This wire, experimental wire, gets stretched, and so its length increases. And when the length increases, this pointer will move down, and so we can measure that increase in the length. So students, I hope you understood about this experimental arrangement. When the force is increased, a stress is produced, because you know that stress is force acting per unit area of cross section of this wire. So when the force increases, there produces a stress, and when the length changes, there is an strain. So strain is change in length upon original length. So stress and strain, they are produced, and by noting down that observations, we can plot the graph of stress and strain. So now students, the relation between the stress and the strain for a given material under tensile stress can be found experimentally. Tensile means the stress which leads to increase the length of the material, either increase or decrease. So length changes when this type of stress is produced. Now, in a standard test, that is an experiment of tensile properties, the test wire is stretched by an applied force, means to study the properties of materials. This experiment is done. And so the fractional change in the length and the applied force needed to cause the strain are recorded. So during the experiment, we have to record the observations. Here in the experiment, the applied force is gradually increased in steps and the change in the length is noted. The relation between the stress and strain can be studied by plotting the graph of stress versus strain, and here the strain is taken into percentage. So percentage strain is plotted on this graph. So here the graph is shown. So now students, according to this graph, initially what happens, as the stress increases, strain also increases, and you can see when the graph is plotted, that is a straight line till point A. The stress and the strain, they are directly proportional to each other from point O to point A. The graph obtained from the observation is a straight line. So it is clear that in this region the material obeys Hooke's law, because according to Hooke's law, stress is directly proportional to strain. So up to some extent, this is proportionality is valid or true. But what happens if the strain and the stress are further increased? So once again, if we go on increasing the mass, then what happens? Now the graph obtained from A to B is not a straight line. You can see it is a curved path or a curved graph. So here after A, the Hooke's law is not obeyed, but still the material till point B behaves elastic. Means once again, if we go on removing the masses which are suspended, then what will happen? That material will come to its original condition and it will regain its original dimensions. So students, here till point A, it obeys the Hooke's law, that is stress and strain, they are proportional to each other. So this point A is known as proportionality limit or proportional limit. But after A, it is a curved line. So there, this proportionality limit is not obeyed. So Hooke's law is not obeyed from A to B. Here, this B point is known as yield point. Means till this point, the material behaves as an elastic. And if the masses are removed, then once again the original dimensions are obtained. Now students, what happens if after obtaining this point B, once again if the stress is increased, that means the masses are increased in the pen. So in that case, what happens? We'll get the curve in this way. On increasing the mass, now the strain is more. You can see the graph is like this. It is more horizontal. Earlier it was more vertical. So stress was more and strain was less. But after B, you can see the graph is like this till D point. So in that case, if you will increase a little mass, then also the change in length will be large. And change in length is large means strain is also large. Now students, here from point B to point D, after increasing the mass at any point, after any point, suppose point C, between B and D, at any point in between that, suppose this point C we have taken in between B and D. If you will once again remove the masses, then now the permanent strain was obtained, means the length of the material has been increased already and it will not regain its original length. So a permanent set is obtained. Permanent set means the length was increased and that will remain as it is. Definitely it will try to regain its original length, but still you will find that some length was there which was increased. So at any point between B and C, if you will reverse the process and if you will unload the pen and if you will measure the length of the wire, there you will find that there is some increase in the length which is permanent, and that is called a permanent set. So this happens till point D. Now what happens after point D? Students, if you will still, now there is no need to increase the mass. You can see the curvature is in the downward direction. Means this limit is obtained for increasing the stress and it is called the ultimate stress. Ultimate means now if you will not increase the mass, then also what will happen? The strain is produced, means the length of the material will go on increasing. Even if you reduce the mass stepwise, then also what will happen? This strain will continue. Remember students, after ultimate stress, if you will decrease the mass stepwise, then also you'll find that now the length is going on increasing. So strain is obtained, and then what will happen? As soon as this point E is obtained, that material, that wire will break. So that point is called the fracture point. Students, this curvature is in the downward direction. Means now no need to increase the stress. Even if you will decrease this stress, then also there will be a change in length. That means increase in the length. And then finally the wire will break. And breaking means it is fracture. So a fracture point is obtained. So students, I hope you understood about the graph. Now let us quickly go through these points which I have written. So from the graph, it is clear that the region between OA is linear, and so Hooke's law is obeyed in this region. And what is Hooke's law? Hooke's law is nothing but is stress is directly proportional to strain. And here in the graph, point A is called a limit of proportionality. Students, keep your textbook open and look at the graph and listen what I am reading. Now, in the region from A to B, stress and strain, they are not proportional to each other because we are getting a curvature from A to B. The graph is curved graph, and so it does not obey Hooke's law. But still, if the load is removed at any point between O and B, the curve will be retraced and the material would return to its original length. That means till point B, that material behaves as an elastic material. And so the point B in the curve is known as elastic limit or a yield point. And the corresponding stress is known as yield stress, denoted by sigma y, y for yield. Now, if the load is increased further after obtaining point B, if the load is further increased, the stress so developed exceeds the yield strength and strain increases rapidly. Now strain is more. Even if you will put some little mass, that means by increasing a little mass also, the strain will be more. Strain means change in length will be more. That is, even for a small change in the stress, strain will be large. And this portion is shown in the curve between points B and D. Now, when the load is removed, say at some point C, this point C is between B and D, the body does not regain its original dimension. Original dimension means here it is length. That is, even when the stress is zero, the strain is not zero. And so, the material is said to have a permanent set. Permanent set means permanently length is increased. And the deformation so caused is said to be plastic deformation. Plastic means permanent strain is obtained, which is not regained back, or we can say which is not elastic. Now the point D on the graph is the ultimate tensile stress, symbolically represented as sigma u of the material. And beyond this point, that is after ultimate strength, additional strain is produced even by reducing the applied forces. And how we can reduce the force? By reducing the loads which are kept in a pen. And finally, what happens? Finally, fracture occurs at point E. And so E is known as fracture point. Now, the stress strain curve vary from material to material. That means if we use a copper wire, then suppose this type of curve is obtained, which is here. But if the wire made up of some other material is used, suppose steel, iron, silver, etc., then these points which are obtained will be at different positions. And so the graph varies from material to material. Now students, this curve helps us to understand how the given material deforms with increasing the loads. Means with the help of experiment, we can find the properties of the material. Which type of property? Elastic property of the material. Now, if the ultimate strength and the fracture point, that is points D and E, are very close in the graph, then that material is said to be brittle. Students, here you can see in this graph that if after point C, if the D point is obtained very earlier, then we can say that the strain is not large, and so that type of material is called brittle. And if after point C, if this D point is obtained at a large distance, that is strain will be more. Strain will be more means the wire can be extended to a greater length. In that case, that type of material are called ductile. So I hope you understood about brittle and the ductile materials. Ductile materials are used to make the wires as well as to make the plain sheets from metals. Now about elastomers. Students, substances like tissue of aorta, rubber, etc., which can be stretched to cause a large strain, are called elastomers. Students, we know that a rubber can be stretched to increase its length at a very large scale, and even when the force is removed, it regains its original length. So such type of materials whose strain is very large, and also it regains its original dimensions after removing the forces. So such type of materials are known as elastomers. Here a typical graph for an elastomer is shown. Here this graph is for the tissue of aorta. This tissue of aorta is found in the heart. It is quite flexible because it pumps out the blood. The blood which is pumping out from the heart passes through the aorta. So that tissue are very flexible, and so for such type of material, if the stress strain graph is obtained, then that graph is like this. You can see at no place it is a straight line. So I have written here as an example, rubber can be pulled to a several times its original length and still returns to its original shape. Although the elastic region is very large, the material does not obey Hooke's law over most of the region. Students, Hooke's law is obeyed when we get the straight line in the graph of stress and strain. But here you can see at no place the graph is straight line. And so we can say that the Hooke's law is not obeyed for most of the region. Definitely for this part from here, this point to this point, it looks a straight line. So for some parts we can say the Hooke's law is obeyed, but mostly it does not obey the Hooke's law. Now students, as I told earlier in a first lecture, that the elasticity or the elastic behavior of the material is widely used in the construction or in the manufacturing, the engineering designs. And so here the region having proportionality limit, or we can say elastic limit of stress and strain curve, is very important. And we know that for proportionality limit, the Hooke's law should be obeyed, and it has a great importance. Students, stress is proportional to strain, that is Hooke's law. And whenever we remove the proportionality sign, we know that we have to put some constant, and this constant K is known as modulus of elasticity. So this K is very important. Now about Young's modulus. Students, the ratio of the longitudinal stress to the longitudinal strain is known as Young's modulus. This is not new actually. We know that stress and strain, if you put equal to sign, there is a constant K. If we make the subject constant K, then we can write here stress upon strain. So this modulus of elasticity is nothing but it is the ratio of stress and the strain. So if we consider the longitudinal stress and longitudinal strain, then this constant is written as y. The symbol for constant is y when we consider it as a longitudinal stress and longitudinal strain. And this y is known as Young's modulus because the experiments on the linear objects was done by the experiment named Young. So it is clear that the ratio of the longitudinal stress to the longitudinal strain is Young's modulus. So according to definition, we can write y is equal to sigma L upon epsilon L. But we know that sigma L, that is stress, is force per unit area, and this epsilon is change in length upon original length. This we have studied. So putting this sigma L and epsilon L from these equations, we get y is equal to F by A, which is this, upon delta L by L, which is this. And then simplifying, we get y is equal to FL upon A delta L. This step. After this, we can easily get this step. Now students, unit of this Young modulus y is same as stress, that is Newton per meter square, or this can be called as Pascal. Students, we already know that strain is unitless. So if this is unitless, then definitely unit of y and sigma must be same, and unit of sigma is Newton per meter square, and so the unit of y is Newton per meter square. I have written a note here that Young's modulus of steel is comparatively larger than the other materials, and so is more elastic. Students, if I ask you, I have a rubber, an elastic rubber of length, suppose 1 meter, and I have a steel wire or steel rod of length 1 meter, then which is more elastic? If you think that rubber can be stretched more by applying the force, and if the same force is applied to a steel rod, it cannot be stretched as that of the rubber. So if you think that this rubber is more elastic, then it is not true. Steel rod is more elastic because elasticity is based on the ratio of stress upon strain and not how the material is stretched. If it is stretched a very large amount, then it is elastic, so it is not true. So steel is more elastic than a rubber. And so this is the reason that steel is preferred in heavy duty machines and in a structural design. We know that for the construction of building, bridges, etc., the steel rods are used because it is more elastic than other materials. Now example number 9.1, given a steel rod, its radius of cross section is 10 mm, length of the steel rod is 1 meter and the force applied at one end of the steel rod, you can see here at one side it is fixed, and from the other end when it is applied a force, then what will happen? There will be a change in length. So here force applied is 100 kilonewton and we want to find the stress produced in the rod, the strain in the rod, and the change in the length. Young modulus for steel is given here. Students, young modulus for different materials are given in a table in your textbook. So this value will be given to you. So now let us first find the stress. According to definition, stress is force per unit area. Force is given 100 kilo. Kilo means 10 raised to 3. So 100 kilo Newton. And area, cross sectional area. This is the area, cross sectional area. And it is a circular. And so area A is equal to pi r square. R is given to us. And so pi, that is 3.14, and radius, how much radius is given? 10 mm, means it is 10 millimeter. Milli means 10 raised to minus 3. So 10 into 10 raised to minus 3 meter, because when we put the values, that should be in SI system. And so value of R is kept here. Now 100 means 10 raised to 2, and here already 10 raised to 3 is there. So powers are added. So 3 plus 2 is 5. So in numerator we obtained 10 raised to 5. Now in denominator, that is here 10 into 10 raised to minus 3. Here 10 means it is 10 raised to 1. And power minus 3 and plus 1. So what will get? 10 raised to minus 2. But there is a square also. So squaring this, we will get 10 raised to minus 4, because 2 into minus 2 is minus 4. And so is here. 3.14 is as it is. Finally, we can get sigma is equal to 3.18 into 10 raised to 8 Newton per meter square. Now, first we will find C and then B, because to find B easily, we need the value of this epsilon. So now, first we will find the strain. According to Young's modulus, y is equal to sigma upon epsilon. Making sigma subject, we will get sigma upon y. Sigma we have already obtained, so we will put here. Young modulus is given to us. Calculating this, we will get 1.59 into 10 raised to 3. Strain is unitless, so here there will not be any unit. This 1.59 can be written as 1.6 up to 1 decimal place. So 1.6 into 10 raised to minus 3. But still, if we put this decimal place here, that means if we write 0.16, then here, as we have decreased here, here 1 power is increased. Increased means already minus 3 was there. plus 1 is added. So 10 raised to minus 2. So we can write this nearly equal to this, that is 0.16 into 10 raised to minus 2. So this is the strain. Now to find the percentage strain, simply we have to multiply this by 100. So when it is multiplied by 100, this 10 raised to minus 2 and this 10 raised to 2 cancel. Remained is 0.16 but percentage. So this is the value of simple strain and this is the strain in percentage. Now how much elongation is there, means how much length of that steel wire is increased or steel rod is increased. Students, we know that strain is delta L upon L, change in length upon original length. So in this equation, if we make the subject delta L, then we will get delta L is equal to epsilon into L. What is epsilon? Epsilon is this, and original length is given 1 meter, so it is here. So finally we will get change in length as 1.59 into 10 raised to minus 3, but 10 raised to minus 3 means it is milli. So we can write this as an answer, then also it is correct. Or in place of 10 raised to minus 3 we can write milli, so millimeter. So change in length, that is elongation, is 1.59 millimeter. Now example number 9.2. In this example, a copper wire and a steel wire are connected with each other, and they were suspended vertically, and at this end a load is connected. Now what happens due to this load? A force mg is produced. We call that as a weight, and due to this force, what will happen? The length of this copper wire will also increase, as well as steel wire will also increase, and so there will be a increase in the total length. But we know that different wires has different properties. The load applied here will affect the copper wire also, and same to the steel wire, but the change in length of copper wire will be different, and that of the steel wire is also different. Students, here we have to neglect the masses of these wires, means we will consider that this copper wire and steel wire, they are massless. So assuming that these wires are massless, this load will affect the steel wire as well as copper wire equally. That means force will be same for both the wires. Now actual length of copper wire is given 2.2 meter, as well as steel wire, its length is also given 1.6 meter. These lengths are actual lengths, that is before suspending this mass. Diameter of both the wires are same, means this cross sectional is same, and that is given 3 mm. So if the diameter is given, half of the diameter is radius, so radius will be 1.5 mm. Students, here total change in the length of this combined wire is given, that when this load is suspended, the change in the length is 0.7 mm. So this is the total increase in the length. And here we want to find that how much load is suspended, means what is the weight of this load. Young modulus of copper wire as well as steel wire are given. It is given in the table in your textbook. So even in the exam also this will be given to you. No need to remember. So now students, let us start with the Young modulus. We know that Y is equal to sigma upon epsilon, that is stress upon strain. But what is stress? Stress is force per unit area. But this force is nothing but it is weight in the downward direction. So W by A. So in place of sigma, I have written W by A. And strain is change in length upon original length. Let us give this equation number 1. Now students, if we make subject delta L, if we make this delta L subject, then this equation number 1 can be written as LW upon AY. Now here this weight is common for both the wires, as well as this cross sectional area for both the wire is same only. So we can consider W and A as constant. So if we remove these constants, we can write delta L is proportional to L by Y. Simply remove this W and A. What is remained? L upon Y. So we can write this delta L is proportional to L upon Y. Now from this we can take the ratio delta L for copper upon delta L for steel should be equal to LC upon LS, and as this is in the denominator we can write YS upon YC. I hope you understood this. Students, we know that if X is proportional to Y, we can write X1 upon X2 is equal to Y1 upon Y2. So this is similar thing. Now actual length of copper and steel wire are given, so we have kept that values. Young modulus are also given, so we have kept that values also. After calculating this, we will get this ratio delta LC upon delta LS is equal to 2.5. And so making subject delta LC, we can write this as equal to 2.5 delta LS. Let us give this equation number 2. Already we have this equation number 1. Now students, total change in the length, that is delta L, is equal to change in the length of steel wire plus change in the length of copper wire. But change in total change in the length is given 0.7. And what is LC? LC can be written as 2.5 delta LS. Delta LS is common on the right hand side, so that is taken out. What is remained? 1 plus 2.5, and 1 plus 2.5 is 3.5. So now making subject delta S, delta LS, we get 0.7 upon 3.5. So after calculating this, we'll get change in length of steel wire equal to 0.2 mm. Let us give this equation number 3. Students, remember our aim is to find W. So this all we are doing finally to obtain W only. Now from equation number 1, we can write this equation number 1 for steel wire also, or for the copper wire also. If we want to write this equation for the steel wire, then we have to write Y for steel. Weight is same, cross section area is also same. So here what we have to make change on right hand side, change in length of steel and original length of steel. So we can write this equation for steel wire. So I have written that equation for the steel wire. Students, you can write for the copper wire also and put the values. You will get the same answer. Here I have used for steel wire. After that, simply make W subject in this equation. You will get this Ys delta Ls A upon Ls. Now, all these values are known to us. So just put these values. Area is pi r square. So this is pi and this is the radius of the cross section of the wire. So we have kept all the values. Using calculator you can calculate it and you will get this as nearly equal to 1.77 into 10 raised to 2 Newton. If you round up this value up to one decimal place, then you can write W is equal to 1.8 into 10 raised to 2 Newton. Unit is Newton because this weight is nothing but it is the force in the downward direction, which is mg. Now example number 9.3. Here given that in the formation of human pyramid, students, in a circus this type of act is shown. This is called a human pyramid. Here you can see there is a person lying here on a table and the other persons, with the help of some instruments, that is some tables and all, they used to form a human pyramid. So this type of concept is given here. So it is clear that the weight of all these persons is on the legs of this person which is lying here. So on both the legs he bears all the weight. So students, here it is given that the combined mass of performers as well as tables which are used is 280 kg. This is the total mass. And the mass of the person lying at the base is 60 kg. So what is the total weight on the legs of this person? We have to subtract the mass of this person, which is 60. So 280 kg minus 60 kg. So what we'll get? We'll get the mass on the legs of that person lying at the base is 220 kg. So this weight is on his both the legs. Here this is the mass, and if we want to find the weight, then weight is mg, mass into g. So mass is 220 and g is 9.8. So this much weight is on his both the legs, 2156 Newton. Now if this is the total weight on both the legs, so force experienced by each thigh bone, because this weight will be on the bones of this person, and this thigh bone is known as femur. So this thigh bone will experience the force, and due to that what will happen? There will be a stress as well as strain produced in the bones. So now students, here the force experienced by each thigh bone, this is the total force on both the bones. So on one bone it will be half of that. So each bone will experience 1078 Newton force. Here given that the length of a thigh bone is 50 centimeter and its radius of cross section, that is this or this, is 2 centimeter, and given in table 9.1 that the Young modulus for a thigh bone is 9.4 into 10 raised to 9 Newton per meter square. Now here what we have to find? We have to find the change in the length of this thigh bone, because due to this weight the thigh bone will experience compression. So there will be a compressive strain, and so length of the bone will decrease a little, and that we have to obtain. So now starting with the Young's modulus, we know that Y is equal to stress upon strain. Stress is force per unit area and strain is change in length upon original length. Here this area is pi r square. So in this equation, making subject delta L, we will get FL upon AY. Now quite easy, simply put all the given values. Force on each thigh bone is 1078 Newton. Actual length of thigh bone is 50 centimeters. So 50 into 10 raised to minus 2 meter. We have converted centimeter to meter. Area pi r square. This is value of pi, and radius is given how much? 2 centimeter. So we have to convert this into meter. So to convert centimeter to meter, 2 into 10 raised to minus 2 meter, and this can be written as 0.02 meter, and so I have written 0.02 and square because it is square of r. Young modulus is given 9.4 into 10 raised to 9. After calculating this, you will get this value, approximately 4.55 into 10 raised to minus 5 meter. This can be written as 4.55 into 10 raised to minus 3 into 10 raised to minus 2 also. But 10 raised to minus 2 meter is centimeter. So in short, you can easily understand that this value can be written in terms of centimeter as 4.55 into 10 raised to minus 3. Students, here this is in meter we have converted this into centimeter. So what we obtained? We obtained change in length. So fractional decrease in the length of thigh bone. Delta L upon L is the fractional change in the length. As L is given in centimeter, that's why we have converted this also in centimeter. So now just putting this value of delta L and L, we will get this as 9.1 into 10 raised to minus 5. It has no unit, remember, because this is a fractional change. Now if you want to convert this into percentage change, then simply multiply this value by 100. So multiplying it by 100, we will get 9.1 into 10 raised to minus 3. This can be written as 0.009 percentage. So students, it is clear that, see, in percentage change, it is very small. So there will be a very small change in the percentage length. Students, I hope you understood about this example as well as the topics of today's lecture. Still, if you have any doubt, you can ask me.